In our course on dams and slopes in mining geotechnique, I find that one of the more challenging topics for students and for professors for that matter is the issue of the behavior of soil during shearing and the shear strength of soil, which essentially for the most part dominates much of stability, certainly your classic slow stability problems and things like that. So I'm just going to review some of the important and maybe challenging concepts about the behavior of soil during shear. Okay, first off, let's talk about what I'd like you to know. Okay. And these are the main topics, just to focus your attention just a little bit. Okay. Strength parameters. So what measures we use to define the strength of the soil in shear. Volume change during shear. And associated with that is pore pressure change during shear. Probably one of the most critical is to understand the distinction between drained and undrained shear strength. And this is kind of at the heart of this topic. That's one of the most important things we want to know for the practical aspects of which condition we have when we're talking about the stability of a slope or a dam. And it's also one of the more challenging issues, I think, maybe in your intro to soil mechanics class. You probably talked briefly about the different kinds of testing, but not so much about the details of what is truly going on. So we'll explore that a little bit more. We'll also talk about testing to determine the strength parameters. And sort of the different analysis methods that encompass all this, all of these topics into it when it comes to the practical analysis. Maybe not methods, because that might be confused with limit equilibrium and things like this, but the approach, whether it's drained or undrained. Really what I'm referring to, if it's an effective stress analysis or total stress analysis. Okay. Now there's a couple things to keep in mind, right? Just a little bit of a review. And basically, at the start of this course, I said there's three main equations that I think are essential for this class, and essentially that's what we're going to talk about here. So it's important to understand essentially effective stress. Effective stress is the total stress minus the pore pressure. And then what is the pore pressure comprised of? It is comprised of a static component, basically due to sort of its location below the water table or phreatic surface, and the excess pore pressure, which is the pore pressure that is built up in the soil due to changes in loading. And that is the pore pressure component that dissipates during consolidation. So you might have to have a little look at your consolidation notes. Okay, and then of course we need the Moore circle concepts, right? Where you have a maximum shear stress and the major and minor principal stresses. Okay. And the Moore-Coulomb failure criteria. Which is tau at failure is equal to the cohesion plus the normal stress on the plane tan of phi. And these are in terms of effective stress parameters. And just a little sketch here to remind you. Okay. And your failure criterion there, defined by these shear strength parameters of C prime and phi prime. So everything is in an effective stress configuration. All right. So first thing we're going to do is talk about drained behavior. Okay, before I get into that, I should remind you the difference between drained and undrained behavior. Okay, essentially, whether a soil is drained or undrained has nothing to do with really whether it's above or below the water table. It really has to do with how fast water drains out of the element of soil. Or really, it's about how fast the excess pore pressures from loading dissipate. If they dissipate very quickly and no excess pore pressure really builds up, then you have a drain scenario. No excess pore pressure really in the system. If the loading rate is so fast that the excess pore pressure does build up, and therefore through effective stress it affects the failure behavior, then it's an undrained condition. So the drained behavior is really, a good example is sand or gravel. But really, it's kind of a relative. It really depends on the loading rate and the hydraulic conductivity of the material. So first, let's just talk about a cylindrical specimen being tested. And we'll put some axial loading on it, sigma A. Okay. And we'll say that water can flow freely. All right, and the loading rate is slow enough that the water can exit it and dissipate the excess pore pressure quite easily. So there's no excess pore pressure. Or UE equals 0. Fast dissipation of UE. Okay, so essentially, when we look at effective stress in that case, the excess component is basically going to be 0. So that doesn't mean you don't have any kind of water pressure, but you just have the static kind, right, which is usually pretty straightforward. Depends usually on the depth below the water table and other factors about seepage and so on. Okay, so when you do some testing in a drain scenario, right, you end up, consolidating it at different levels and develop some circles representing each test. And from that, you can fit a curve or a line, which is a failure envelope, to define the shear strength parameters. Okay. So like you said, although the excess pore pressure is 0, US can still exist, the static portion, and has to be accounted for. Okay, for example, if you have a soil and the water table and you're located at some depth below it, okay, you have a hydrostatic gradient, gives you the static water pressure at that point. But we're assuming that any loading that happens, the excess pore pressure is 0. Okay, so US plus UE, which goes to 0. Okay. All right. So let's draw that more Coulomb plot again, right? And so you had a failure envelope up here, and your stress state puts you over here in a happy place, which is well below the failure envelope. Nothing is touching it. But if you have enough excess pore pressure, or sorry, static pore pressure, that can cause well, that's a very crude circle, but you get the gist of it. That can cause the stress circle to hit the envelope. It can induce yielding. So that is the static pore pressure component. So that is how pore pressure has to be considered in a drained scenario. Okay. Now we're going to talk about shear-induced volume change. For the drains case. So let's draw our specimen again. Axial load. And water is allowed to flow out. And say in this case we're also measuring all the volume change that occurs. And let's draw down here two other plots lined up with each other. Let's make the horizontal axis the axial strain, okay, or the vertical strain while you're testing it. So that's measuring the displacement. And we'll make the top plot change in volume, where positive change in volume, in this case we'll say is expansion. And the bottom negative will be compression. Okay, and the other plot below it will have change in excess pore pressure, positive and negative. Okay, so if the water is allowed to flow out freely and relatively quickly relative to the loading rate, then the excess pore pressure remains zero as you test this thing in axially. Okay, so 0. No change. But what happens to the volume? Okay, there's two primary cases, and to be honest, there's everything in between. But let's talk about the two most common cases. One is the case of a relatively loose sand. And what happens when you shear a relatively loose sand is that as the shearing plane starts to move and shears everywhere inside, tends to want to shear everywhere inside, you have a tendency for the grains to sort of realign themselves. And in that way, if it's loose, as it shears, the voids start to get smaller and it realigns to a more compact state. So the volume change is negative. Okay, it just compacts and compacts and compacts for a loose sand. Okay. Now a dense sand, it's already quite compact. There's not a lot of excess void spaces. What happens when you start to shear it is initially maybe it compacts just a little bit, but then what happens is the particles have to move around each other in order to continue to shear, and that causes them to dilate or increase in volume change as the pore spaces start to get bigger. So it compresses a bit and then it changes direction and dilates. Okay. And that's a dense sort of sand or other type of granular material. Okay. So we have dilation and contraction. Or dilative and contractive behavior. Okay, so the bottom line of all this is it has no real change in pore pressure, but a change in volume. And change in volume doesn't really have a big effect on effective stress. So really this, in a drain scenario, doesn't have a real effect on the strength. Okay. So, what's the practical implications of this? Well, it's relatively straightforward lab testing. To get the drained parameters, triaxial, or direct shear, or something like that. And we use the drain shear strength parameters, or effective stress parameters. Shear strength parameters. C prime and phi prime. And the excess pore pressure is 0. And when we carry out an analysis for slopes and so on using these approaches, we still have to use the static pore pressure. So everything is done in terms of effective stress, and we call that an effective stress analysis, or ESA. So that's the gist of how soils behave in a drained manner. Now let's talk about undrained behavior. It is just a little bit more complex. And remember, this is when loading rate is faster than pore pressure can dissipate. And so that's like conditions where the hydraulic conductivity is quite low for the most part. So a clay is a good example of a material that is often behaves in an undrained manner, but not always. Again, it's relative. It depends how fast it's being loaded relative to its hydraulic conductivity. So let's draw another specimen over here, okay, and axial loading. In this case, no water can flow out, okay? No water flow. All right, so if no water can flow, definitely some pore pressures are going to be able to build up. But also because no water can flow, right? The voids can't change in size. They're full of water. The water's not going anywhere, and we're assuming that the water and the soil is incompressible. So the voids cannot change in size. Therefore, the overall sample experiences no volume change. So, the drain case, we have no excess pore pressure, but we have volume change. The undrained case, we can generate excess pore pressure, but there is no volume change occurring. So because no dissipation of pore pressure occurs, all all the additional loading, like the axial loading in this little sample here, goes to the water, right? If you remember consolidation theory, all the extra loading originally goes to the water pressure until consolidation occurs, and then it starts to shift from the water to the soil grains. And eventually, once it's fully consolidated and the excess pore pressure is zero, all the load is on the soil grains through effective stress, and none of it is in the water through the excess pore pressure. Okay, so if we look at that in the context of effective stress equation, effective stress is the total stress minus the pore pressure. In this case, we have no change in effective stress. But instead, all the change is due to the total stress and the pore pressure. So these have to change together. Let's have a look at that in terms of the failure envelope and what that means. I think you remember what this looks like from your intro soil mechanics class, but we'll talk a little bit about why. So, essentially, if you do an undrained test, you get a certain circle that corresponds to failure. Now, if you increase the confining stresses around your specimen and you do the test again, like I said, all the stresses go to the water and none of the stresses go to the soil. So the soil is completely unaffected and essentially has the exact same strength and fails in the exact same way at the same shear stress. Okay, so that results in a more or less a perfectly flat failure envelope. So the undrained friction angle is zero. And so it's often called a phi equals zero analysis. And the undrained shear strength is sort of the intercept of this line with the tau axis, or kind of similar to cohesion. But it's not the same as drained cohesion. That's an important point. It is its own parameter, SU. And it accounts for all the behavior in the sample, including the behavior of the pore pressure, is all accounted for by this one parameter, SU. Some people use different parameters. Well, first, let me write a little note here. Nothing changing in the soil. So it's experiencing the same behavior. So it has the same strength. Okay. So like I was saying, there's different terminologies here. SU is a common approach. Some people prefer CU, and some people prefer CT, where T stands for total stress. So in this case, we're not looking at effective stresses. Simply do the test, locking all the water pressure in, and find out what the response is in terms of the total stress scenario. And all the pore pressure behavior is sort of inherent within the test, and we're not tracking it because, as I'll show you in a minute, it's kind of complicated. Okay, and so the other parameter, some people use phi u and or phi t. Okay, so there's some different terminology can be used. The most important thing to remember is that the shear strength is equal to the undrained shear strength. That is the bottom line. All right, so what's going on during one of these tests? Okay. In the drain test, we had a lot of volume change occurring and no pore pressure changing. In this case, it's the opposite. Okay, so we have shear induced pore pressure change. For undrained loading. So let's draw our little specimen again. Axial loading. And there's no drainage, but we are measuring the pore pressure response, but no water's flowing. And no volume change. So those are the conditions. All right. So let's draw our little couple of plots again. Okay, one over the other. And again, the horizontal axis is axial or vertical strain. We'll make the top plot be change in volume, dilatant and compressive. And the bottom plot will be change in excess pore pressure. We have increasing pore pressure at the top and decreasing pore pressure or negative excess pore pressure on the bottom. Okay, so there's no volume change as you actually load this thing, right? So, 0. Now the pore pressure is a little bit complicated, and it relates to, in some way, the volume change characteristics of the drain test. So, in the sand-like material, granular materials, we had two cases, loose and dense. The analogous conditions for a clay-like material, if you remember, is really about its consistency, whether it's soft or stiff. And a soft soil is often what we call a normally consolidated soil. And stiff is characterized by an over-consolidated conditions. Okay, so the normally consolidated soil, or soft, has a tendency to have an increase in pore pressure with loading. Okay. Now, if you think about what the drain condition was it wanted to contract, right? So the voids wanted to contract. In this case, when no water is allowed to flow in or out of the voids, this tendency to want to contract kind of results in sort of pushing of the grains on the water in the voids. And that causes the pore pressure to want to increase during shearing. So you imagine it, the grains want to contract. All the voids are fully saturated, full of water, and the water cannot escape. You're shearing it. It wants to go to a more compact state, but it just cannot. And so there's a pressure buildup inside of the pores. We're increasing excess pore pressure. So it wants to contract, but it can't. Okay, now think about the dense sand. First it contracted a bit and then it dilated. Okay, and so if it's not allowed again to change any water in the system, all the voids remain soft. So first it has a tendency to contract. It's pushing on the water, okay, causing an increase in pore pressure. And then it very quickly, the soils have a tendency to want to dilate, right? Find a more open structure. And in a sense, it starts to pull on the water in the voids as it has a tendency to want to dilate, but it cannot. And so the pore pressure starts to decrease. Okay, and you have a negative change in pore pressure. Okay, for over-consolidated soils or stiff soils. Clays, I should say. Okay. So it has a tendency to want to change volume, but it just can't. Okay. Because all the water is locked in. Right. Now in this case, contrasting to the drain case, we have a lot of excess pore pressure change, which does have an effect on the shear strength. Through the effective stress equation. Okay. Which is connected to the failure criterion that we use. So if you look at this plot here of excess pore pressure, basically the pore pressure is changing in a fairly complicated way as it's loading. And it's very sort of difficult to know exactly what is going to happen in a field scenario as shearing induces. So instead, we simply carry out the test and come up with the undrained shear strength, which incorporates directly the changes in pore pressure going on inside of the specimen. And we simply look at it in terms of the total stresses being applied to the specimen and how much it can handle. And all the effective stress, pore pressure behavior is implicit to this. So we basically simplify it all down, okay? So the excess pore pressure is changing. Shearing progresses. And it's hard to judge. The impact on shear strength. So we test in an undrained configuration in the lab. Where no water is allowed to drain out of the triaxial cell, for example. And we use the undrained shear strengths in our designs and analysis. Pore pressure change is incorporated into SU. So we don't explicitly use it in the calculations. Instead, we just use the total stress values for the problem and compare it to the undrained shear strength. And we call this a total stress analysis. So that's how undrained behavior works and how we make use of it in practice. And so one of the biggest things that a person has to appreciate, an engineer has to appreciate when they're doing design calculations for slopes and dams, is when to use the total stress analysis and when to use the effective stress analysis. And that's something that we will talk about in further classes.